Good morning, everyone, and welcome to today's lecture. This is Thermodynamics lecture number 7. In the previous lecture, we had dealt with thermometry, the branch of physics which deals with the measurement of temperature. And we had seen the entire thermometry can be done with two simple formulae. Do we remember those two formulae? The first formula was any reading on any scale minus the freezing point of water divided by the boiling point minus the freezing point is a constant. Do we remember this? Do we remember this? For Celsius scale, the formula becomes C minus 0 upon 100 minus 0. For Fahrenheit scale, the formula becomes F minus 32 upon 212 minus 32. And for the Kelvin scale, the formula becomes K minus 273.15 divided by 373.15 minus 273.15. We all recollect this? We had also seen that Celsius scale also has 100 division and Kelvin scale also has 100 divisions. A change of 1 degree Celsius is same as the difference or change of 1 Kelvin. A change of 9 degrees Celsius is same as the change of 5 degree Fahrenheit. Do we remember this? This was the first formula that we had seen. The second formula that we had seen was for thermometers, and we had seen what? Any value x at temperature T minus the value of x. It can be the length, it can be the volume, it can be the pressure, it can be the resistance. The value of x at the freezing point divided by the value of x at the boiling point minus the value of x at the freezing point. If I multiply it by 100, that will give me the temperature in degrees Celsius. If I multiply it by 180, it gives me the temperature in Fahrenheit. Do we remember this? Okay, so the entire thermometry chapter can be done with these two formulae. So remember, any question that comes in thermometry, either it has to be done by formula number 1 or it has to be done by formula number 2. That is the end of story. Please remember this. I'm expecting a question to come this year in this particular topic, and that is why we have done this. So now let us move ahead into today's topic. And today's topic, if you would have guessed, it would be something known as this. What is this? This is known as thermal expansion. Have you heard about the term thermal expansion? We've already used thermal expansion in the previous topic when we had found out how to make a thermometer. We have used thermometric property. We have used the property of volume of a liquid. We have seen that the volume of a liquid increases when the temperature increases. Yes or no? We have seen that. Yes. And that is what is known as thermal expansion. If you increase the temperature of any body, the only exemption is water from 0 to 4 degrees Celsius. When you increase the temperature, volume does not increase. the volume decreases. Am I audible and visible to all of you? Okay. So apart from water from 0 to 4 degrees Celsius, everything expands when the temperature is increased. If you talk about solids, all solids, not liquids, all solids are found to expand on heating. This is known as thermal expansion. Now, why do solids expand on heating? This is the reason why bodies expand on heating. It is because of asymmetry in the potential energy curve. And remember this curve and remember this statement that thermal expansion is due to asymmetry or no symmetry in the potential energy curve. If you look at this curve, can you see this curve? Can you see this curve? This curve is not symmetric. On the left hand side, you can see the curve is very steep. On the right hand side, after this point, the curve has become very less steep and it is not symmetric. It is not similar. This is the point where the potential energy is minimum, and this is the distance between the molecules or intermolecular distance. R is the average distance between molecules. If you heat this body, what happens? The curve on the right hand side takes a dip. It goes below the original value. That means the potential energy decreases, and that is the reason that things will expand on heating. So what you got to remember in this entire discussion is two things that you will mark. The first thing is things expand on heating because of asymmetry in potential energy curve, and the second reason is the same thing explained in the graph. The graph of potential energy versus R is unsymmetric. Do we understand this? I'll give you a minute to note this down. Please note it down. Have you noted it down, beta? Yes or no? Are you noting it down? Okay, I'll give you a minute more. Shall we move ahead? Okay. Now, when we talk about thermal expansion of solids, and I hope you can see this, bacha. Thermal expansion in solids. Remember, we are talking about liquids. We are not talking about gases. Gases, we have already seen what happens. Thermal expansion of solids. Now I can think it of in three different ways. One is known as linear expansion. One is known as superficial or surface or aerial expansion. You can write a third name, aerial expansion. And the third one is known as volume or cubical expansion. Now, why there are three types of expansion? Now, please remember that they are not of three types. They are basically only of one type. But why we have given it in terms of three ways? Well, take the example of this pen that I have in my hand. Now, every solid body that you see is a three-dimensional body. It has three dimensions. What are the three dimensions? One is the length, the other one is the breadth, and the third one is the thickness. So everyone has three dimensions. Every solid body that you see has three dimensions. But if we take the example of a very, very thin wire, this is a very thick pen, I don't have a very thin wire. Take the example of a simple thread, simple wire. Now this simple thread or a simple wire also has three dimensions. It has a length, it has a breadth, and it has a thickness. But one of these dimensions, which is the length, is very... You can't hear me? You can't see me? What's happening? Everything all right? Sorry, you can't hear me? What is the problem? You can't see anything? Let me know. I am not able to understand. Let me know. Just type it so that I understand. Video and audio stopped, sir. Can you hear me now? I mean, from my end, everything is okay. I can hear my video. I can see my video here also. Okay, now it is clear. Okay, things happen in life. Okay, so what I was telling you, and again, I will repeat myself. I'll go slowly again. Everything has three dimensions. It has a dimension of length, it has a dimension of breadth, and it has a thickness. But if we take the example of a very, very thin wire, and I don't have a very thin wire here, a very thin wire or a very thin thread, it has three dimensions, but the width and the thickness is very small. Now, even though it is three-dimensional, for all practical purposes, we can take it as a one-dimensional body. So, very, very thin thread is a one-dimensional body. Do we understand this? A very thin thread is a one-dimensional body. Now, if I heat this thread, Though it will expand in volume, but the thickness and the breadth is very small. It will expand in volume, yes, but we will take the expansion as expansion in length. And that type of expansion is known as linear expansion. This is the expansion of a body in length. Now, when will body expand in length? When the body is very, very thin, just like a thin wire. It will expand in volume, but we take it as expansion in length. Do we understand this? So this type of expansion of a very thin wire, and I will write it here, and I hope you are noting it down. This expansion of a very thin wire, which is a three-dimensional body, but we are taking it as one-dimensional, is known as linear expansion. I hope you are noting it down. The second type of expansion is, I will write on linear expansion 1D bodies. 1D means one-dimensional body. One-dimensional body only has one dimension. It has three dimensions, but we take it as one dimension. Now take the example of this. This is my Bijli ka bill. Take the example of this sheet of paper. Now this sheet of paper also has a volume. It has a length. It has a breadth. It has a thickness as well. But the thickness of this sheet is very small compared to the length and the breadth. In other words, instead of taking this as a two-dimensional body, instead of taking this as a three-dimensional body, I will take it as a two-dimensional body. Do we see? Am I clear? We see this as a two-dimensional body. When it expands, it will expand in area. For a two-dimensional body, just like a sheet of paper, it expands in area. We take that expansion as areal expansion or superficial expansion. Do we understand this? This type of expansion is known as areal or superficial expansion. The third type of expansion is for any body which has a length, which has a breadth, which has a thickness. It will always expand in volume. Such type of expansion is known as volume expansion or cubical expansion. Do we understand this? I give you 1 minute to write this, then we will illustrate this. This is a very simple chapter. It only has one formula. If you can remember that formula, bacha, one question will come and that will be simple formula based. I'll give you a minute. I'll give you a minute to note it down. I hope you have noted it down, everyone. Now let us talk about linear expansion. Let us talk about linear expansion. Remember, when I talk about linear expansion, I am talking about one-dimensional bodies. I hope you understand the meaning of one-dimensional body. Please raise your hand. You understand one-dimensional bodies? Okay. Now, this is a one-dimensional body. This is a thin wire. The length of this wire, let us say, is L naught. Naught meaning initial, zero, initial. This is a thin wire whose length is L naught. Now what I have done is I have increased the temperature. Now, once I increase the temperature, what happens? Once I increase the temperature, what happens? The length increases. And as you can see, this is the change in length. Change in length is denoted by delta L. Delta means change, L means length. So now, from here to here, the length is L naught. And the length has changed by delta L. Now, this change in length delta L, it depends on the type of material. If it is made up of iron, it will be different. Silver, aluminium, gold, different metals will expand differently. Do we understand this? It will also depend on the initial length L naught. If the initial length is more, it will expand more. If the initial length is less, it will expand less. Do we understand this? It will also depend on delta theta. Delta theta means change in temperature. If the temperature is increased very much, it will expand more. If the change in temperature is very less, it will expand very less. So it depends on three things. Please remember these three things. A question can come on what all factors the change in length depends on. Now, if I keep all these things together, I can write a simple formula. Delta L will be equal to alpha into L naught into delta theta. I hope you can see this formula. Alpha into L naught into delta theta. This alpha is a constant. This alpha is a constant which depends on what type of material, what type of body we have. This constant is known as the coefficient of linear expansion. This is known as the coefficient of, linear expansion. Are you following me or have I gone too fast? This alpha is known as the coefficient of linear expansion. Are we there on the same bus with me? Or have the bus left the station? This alpha is known as the coefficient of linear expansion. What is this delta L? This delta L is the change in length. L naught is the original length. Delta theta is the change in temperature. Now, if I talk about the new length, and if I call this length L as the new length, the new length will be equal to L naught plus delta L. Do we understand this, bacha? This new length L will be equal to L naught plus delta L. I hope everyone is following me. Yes or no? Okay. Now, how do I get the value of this L? I just put the value of delta L. So L becomes L naught plus alpha L naught delta theta. If I just write, taking L naught constant, L is equal to L naught into 1 plus alpha delta theta. L is equal to L naught into 1 plus alpha delta theta. Do we all understand this? I'll give you a minute to note this down. Then I'll give you 2 or 3 simple points about this that you got to remember. If you can remember those points, well, this topic will be over. I'll give you a minute to note this down. We have noted this down? Okay. Then point by point, I will just write what you got to remember. Point number 1, what you got to remember is change in length delta L will be equal to alpha L naught into delta theta. Point number 1. Point number 2, I can write this alpha as delta L divided by L naught into delta theta. This is not a different formula. It is just derived from formula number 1. This alpha is known as coefficient of linear expansion. Its unit is, SI unit is 1 by Kelvin. Length and length will get cancelled. This SI unit is 1 by Kelvin and its dimension is 1 by K also. Okay, raised to the power -1. Remember this. Point number 3, the total length, new length L will be equal to L naught plus delta L. The fourth formula is, this L can be written as L naught into 1 plus alpha delta theta. Do we all understand these 4 points? Yes or no? But if you understand these 4 points, the rest of the topic becomes very simple. So write these 4 points. Have we noted it down? Okay. Now that brings us to the second type of expansion, which is known as aerial or superficial or surface expansion. In this, what will happen? Instead of length, things are going to expand in area. So this is the original body, and now we are talking about two-dimensional bodies. Do we understand this? Its initial area is A naught. Now what I am going to do is, I am going to heat it up. When I heat it up, it becomes like this. The red one is the heated body, and as you can see, the area has increased. Can you understand it from the diagram that I have created? The area has increased. The area has increased. The change in area is delta A. Do we see this change in area as delta A? Now, I can write the formula for this, and I will not repeat whatever I have said. What will be the formula for change in delta A look like? It is similar to what we have seen already. I'll give you a minute. If you can think about what will be the formula for change in area. In the first case, we have seen the formula for change in length. Can you now tell me what will be the formula for change in area? Think. It's similar to what we had already seen in length. What will be the formula for change in area? And the formula will look like this. It will depend on the material. So we use beta. It will depend on the area, initial area A naught, and it will depend on the change in temperature delta theta. So the formula will look like this. This beta depends on the material, and this beta will now be known as what? We know the answer. It will be now known as the coefficient of aerial or superficial or surface expansion. Do we understand this? Can I have some raise hand if you understand this? I'll give you a minute to note it down. Have you noted it down, beta? Then again, we will note down the 4 formulas for this. Formula number 1 for this is change in area delta A is beta A naught delta theta. Formula number 1. Formula number 2, the value of beta will be equal to change in area divided by the original area divided by delta theta. The unit for this will be same, and it will be equal to 1 by Kelvin. Do we understand this? Formula number 3. You are not seeing it. Oh, sorry. The screen was paused. So, formula number 1, formula number 2, formula number 3 will be the new area A will be equal to A naught plus delta A. You can write this new area A as equal to A naught into 1 plus beta delta theta. So as you can see, if you remember the first formula for change in length, you can remember the formula for change in area. Is it clear to everyone? I'll give you a minute to note down these 4. Have you noted it down? Great. I love that spirit. Now we come to the last of this thing, volume expansion. Again, if you heat anything, it will expand in volume. We straight away move on to the formula for this without wasting any time. What would be the first formula? The first formula would be for change in volume, delta V. We have used alpha for linear, beta for aerial, and I will use gamma for volume expansion. So gamma V naught into delta theta, where gamma, what is this gamma known as? This gamma would be known as the coefficient of volume or cubical expansion. You can find out the value of this gamma. This gamma will be delta V upon V naught into delta theta. And remember, the units of this gamma as well as alpha or beta are same. It is 1 by Kelvin. SI unit I am talking about. If I talk about the final volume V will be equal to V naught plus delta V. And as I said, if you remember any one of those formula, you will be able to make out the rest of this. Final formula V will be V naught into 1 plus gamma delta theta. I'll give you a minute to note these formulas down. I hope you have noted it down, bacha. Yes. Okay. I hope all of you are in high spirits. Looking so. So again, this is what we have discussed so far, and what you see over here, bacha, is the differential form of alpha. Instead of delta L by delta T or delta theta, it is written as dL by dt. Do we understand this? So just this is from your sheet. This is from the sheet that you have. So you can note down this formula right in the side of the formula that we had written for alpha in terms of the derivative formula or the differential formula. Similarly, we have the derivative or the differential formula for beta. Similarly, we have the derivative or the differential formula for gamma. Again, change in length delta L, the formula is given. We have already noted that. Change in area formula is already given. We have noted that. Change in volume, the formula is already noted. The only thing that you have to note from this sheet, this is there in your sheet. Note it there, not in the sheet, note in your notes wherever you have written the four formulas. I'll give you a minute to do it. I hope you have noted this down, everyone. Then comes the formula for final length. I have already told you the formula final length, final area, and final volume. What I want you to note it down right now is the relation between areas and length. Obviously, we are talking about a square sheet. New area divided by the original area will be equal to new length divided by original length ka square for a square sheet. Do we understand this? For a cubical sheet, if I talk about volume, new volume divided by the old volume, initial volume will be equal to new length divided by the original length cube. We are talking about the cube, the volume of a cube or area of a square plate. Do we understand this? Please note down these formulas. Which formula? A dash by A wala and V dash by V. Have you noted this down? Yes. Then comes the next formula, next concept, and the next concept is this one. What is the relation between alpha, beta, and gamma? And you should not forget it. The ratio of alpha is to beta is to gamma is 1 is to 2 is to 3. That means my beta is 2 times alpha, my gamma is 3 times alpha, or I can write any relation. Gamma will be 3 by 2 beta or beta will be 2 by 3 gamma. It's a very, very important formula. You should never, ever forget it. Please note it down. The derivation is also there in the sheet. It is not required, so I am not doing it. The relation is important and you will note down the relation now. Shall we move ahead in life? Okay. Now, if the question is not numerical in this chapter, the question can be on a bimetallic strip. Now, what is a bimetallic strip? It is sometimes used in a switch where we need to switch on or switch off something based on the temperature. For example, your AC. You don't have a AC in the classroom, but you might have AC at home. Now this AC, the normal AC, which is not an inverter one, even an inverter one, it keeps on switching its load depending on the temperature. If the temperature is high, it will work at a higher load. If the temperature is low, it will work at a lower load. Or your normal AC, which is not an inverter one, it switches on and switches off. Yes or no? We understand this. When the temperature is high, it will switch on. When the temperature is low, it will switch off. It works with a thermal switch, something that works on temperature. And this is that thing that works on temperature, which is known as a bimetallic strip. Now, what is a bimetallic strip? It is a strip which consists of two metals. And I will enlarge this view and I will show it to you how it looks like. I hope you can see it. Again, it is given in your sheet. I hope you can see this. You can see this bimetallic sheet, yes or no? Okay, now what you see is this here is it is made up of two metals. One is my copper gentleman, other one is my iron gentleman. Now, at the normal temperature T1, the metallic strip is like this. It's straight like this. Do we see this? Yes or no? But when the temperature increases, now this metallic sheet is bound from here, so they will move together. When the temperature increases, one metal is iron, the other metal is the other metal is copper. They don't have the same coefficient of expansion. They are different metals. They have different coefficient of expansion. Someone will have more expansion, someone will have less expansion. Do we understand this? Someone will have more expansion, someone will have less expansion. So this metal plate, this bimetallic strip, which is like this, it will bend like this. It will bend. It will bend. Do we understand this? It will bend. Now, how will it bend? The metal which has higher alpha will be on the outer side or the convex side. This is higher alpha. Copper has an higher alpha. And the one which has a lower alpha will be on the concave side. Do we understand this? Higher alpha will be on the outer side or the convex side. It will expand more. More length is more. The thing, the metal which has less expansion will be on the concave side. Do we understand this? Have you seen this diagram? Have you drawn this diagram? Same simple question will come here. They will ask you which metal will be outside, which metal will be inside, and you will have +4 here. Else you will get a very sad -5. I hope you have drawn the diagram. Has anyone drawn the diagram? Yes, sir. Kajal, you drawn a diagram? I never saw your hands moving. So must be some. Oh, good, good. Well done. I might not have seen it because you are sitting in shade and I just can't see you. Okay. And they have explained it here in the sheet. You can mark it in the sheet if you don't want to write. Some things can be marked in the sheet. I understand that. But something have to be written because written word is what that matters. The strip will bend with the metal of greater. The spelling of greater is wrong. Alpha on the outer side, that is the convex side. This is the entire thing that you need to understand. In words, it is written like this. In diagram, it is drawn like this. To understand it, +4 is waiting for you. I'll give you a minute before moving on to the next question. Remember, what we are doing are simple questions. They are not theory. These are questions that are going to come, and when they come, you will remember sir had discussed this in the class. But what will matter there is whether you remember it or not. Shall we move ahead in life? Have you done this? Okay. Now the next question that comes is based on the expansion of a body with a hole. You can see here, I have a body and it has a hole inside it. Do you see this hole? The circular hole. The circular hole that we have is marked with red. Do you see the hole? Yes or no? Now the question that comes is, what will happen to the hole when the body expands? If I heat up this body, if I increase the temperature of this body as a whole, what will happen to the hole when it expands? Does the hole increase in area or does the hole decrease in area? The same question could be asked for a cube. I have a cube. I have a spherical hole inside the cube. I heat up the cube. What will happen to the hole inside the cube? Will it expand or will it contract? I'll give you a minute to tell me what will be the answer, whether it's a hole in a sheet or whether it's a hole in a cube. When I heat it up, what happens to the area or the volume of the hole? 1 minute, think about it, tell me the answer. So my dear kids, what is the answer? Option number 1, the hole expands. Option number 2, the hole contracts. Which one? Number 1 or number 2? Number 1, it expands. Number 2 is it contracts when I heat it up. And the answer is number 1. Remember, when you heat up this body, the entire body will expand. The hole will also expand. Do we understand this? Can I have some raised hand from everyone that we understand this? Well done. Well done. Then on that note, we're already done with this. We are almost done with this chapter, this topic, and now it is the time for us to do some questions. And the question that is coming up is from your sheet. Example number 1, and this is how the question looks like. It has some value, so it might take some time for you to get the answer. The question that comes in the examination hall may not require you to calculate it. So I also don't require you to calculate it. I just require you to tell me how it is done and what is the final question looking like. For example, if you don't want to calculate, what will you do? 50 centimeters, we can call it as L1 or length of brass, LB. The length of the steel rod is also same, so both the length are same, so you can call that length as L. Alpha of brass is given. Instead of using the values, you can use alpha of brass. Alpha of steel is given, so instead of using the value, you can use alpha of steel. So I need the answer in algebraic form, not in the numeric form. I'll tell you what is an algebraic form. That change in temperature is given as 250 degrees. So instead of using 250 degrees, just use delta theta. Do we understand this? So I just need the answer in the algebraic form. I don't need the calculations because long calculations may not come to you. I'll give you a minute so that you can tell me the answer. And it is already solved in the sheet. So what is happening in the question is we have two different rods. One is a copper rod, one is a brass rod, another one is a steel rod, and I have joined both of these together, and then I have changed the temperature. They are just asking you what is the total change in length. I hope you understand this. I hope you understand this. Two rods, rod number one, rod number two, joined together, and then they are asking you what is the length, change in length of this combined rod. Do we understand this? One is brass, the other one is steel. Have you done this? I'll give you a minute to win it, and I hope you are good enough, sincere enough to solve it. So we are done, and the answer is pretty damn simple. The total change in the system, we have to find the change in length of steel rod into alpha of steel rod into delta theta. We have to find the change in the brass rod, change in the length of the brass rod. Length is same, so I use the same length. Length could have been different, then we would have used different lengths. Alpha of brass rod multiplied by change in temperature. How do we find the total change in length? We don't subtract because both are going to expand. Do we understand this? So the total change in length is this formula, change in length of steel rod plus change in length of brass rod. You can put the values, change in length of brass rod and change in length of alpha rod, and this is the answer that you will get. In the exam, you might be given 4 options. Number 1 option could be like this. Number 2 option could be change in length of brass minus change in length of copper steel. Third option could be change in length of steel minus change in length of brass. The fourth option could be none of these. So you just have to take the correct option. They might not ask you to solve the question. Do we understand this? Only one student has understood this. That is not good. What about the rest? Do we understand this? Please raise your hands and let me know so that I can move forward with the next one. Shall I repeat it again? Okay, let us move on to the next one. And the next one is pretty simple. And again, I don't need the numerical answer. You can just give me the algebraic answer. I have a sheet of brass. 50 centimeter is the length. You can call it as L. 10 centimeter is the breadth. You can call it B. Initial temperature is 0. You can call it theta 1. Final temperature is 100. You can call it theta 2. Theta 2 minus theta 1 is 100. You can call it delta theta. Do it in short steps. The area of the surface changes by 1.9 centimeter square. You can call it delta A. So delta A is given to you, length is given to you, breadth is given to you, change in temperature is given to you. You have to find the coefficient of linear expansion. Can you do that for me? I will give you a minute. I don't want the numerical answer. It might require calculation. I only want the algebraic answer, and your time starts now. Have you got any answers, bacha? I'll give you 1 more minute to think about it. So let us start and solve this question. How are we going to solve this question? We have to find the value of alpha. We have to find the value of alpha. We know the relation between alpha and beta. So alpha is beta divided by 2. This is step number 1. Do we all understand this step number 1? Can I have some raise hand that we understand step number 1? Now the only thing is, can we find out the value of beta? How will I find out the value of beta? Change in area is delta A. Original area is length multiplied by breadth. Length is known, breadth is known. Into the value of beta, into the value of delta theta. So from this equation, I can find the value of beta. The value of beta is delta A divided by length into breadth into delta theta. Do we all understand this? From here, I can find out the value of alpha. Alpha is beta divided by 2. Change in area divided by 2 into length into breadth into delta theta. That is what you call algebraic answer. You can now put the values here and get your answer. What I would suggest as a tip is, if you get a question like this where you have to do multiple calculations, do not do the calculations at every step. You find the final answer and then you do your calculations. What is the benefit of this? If there are any mistakes in the calculation, it will only happen at the last step. You don't have to correct your calculation or to check your calculations at every step. So I would suggest that you do calculations only at the last step. I'll give you a minute to note this down. If you have any doubt, please let me know. Can you move ahead? Have you written this down, beta? Okay. We are done with the expansion of solids. We have three types of expansion of solid: linear expansion, AL expansion and the volume expansion. Now we move on to liquids. Now for liquids, we cannot have a one-dimensional liquid or a two-dimensional liquid, and therefore liquid don't have aerial or linear expansion. They only have volume expansion. Do we understand this? Liquids only have volume expansion, so they only have one coefficient, which is gamma, which is the coefficient of volume expansion. Please raise your hands so that I understand that we understand this. Liquids only have one coefficient of expansion, which is gamma, which is the coefficient of volume expansion. Now, this gamma for liquid can be defined in two different ways. One is known as gamma real. The other one is known as gamma apparent. What is gamma real and what is gamma apparent? Well, I'll first show you the formula for gamma real. Now, what do you mean by gamma real? Whenever we heat up a liquid, it expands in volume. We all know this. The only exception is water from 0 to 4 degrees Celsius. Because when we heat water from 0 to 4 degrees Celsius, it does not expand, it contracts. Do we remember this? Whenever we heat water from 0 to 4 degrees Celsius, it does not expand, it contracts. This is known as anomalous expansion of water. I have been telling you just again and again. Do we remember this? Now, we come to normal liquids or water which is not between 0 to 4 degrees Celsius. When I heat it up, it will expand. This expansion coefficient is known as gamma real or gamma R, which is the real increase in volume. What is the actual increase in the volume? Divided by the original volume. So I can write it as delta V, change in volume, real change in volume, real change, exact change, divided by the original volume V naught, divided by change in temperature. So the formula looks very simple. It is as simple as we had in the previous cases. And what we had in the previous cases, it is delta V R, R standing for real change in volume, divided by original volume V naught into delta theta. Do we understand this? Can I have some raise hand that we understand this? Okay, I'll give you a minute to note down this gamma real or coefficient of real expansion. Have we noted this down? Can I move forward? Have you noted down the formula for real expansion? Okay. We move on to the next thing, which is known as apparent or observed expansion. Now, what is this apparent or observed expansion? You have all might have seen water boiling in a beaker. When you boil water in a beaker, when you boil milk in a beaker, the milk overflows. Now, when you are heating a liquid in a beaker, in a solid body, when you heat it up, two expansions take place. One is obviously the expansion of liquid that you can see with your eyes. Milk coming out, you can see it from your eyes. That is the expansion of the liquid. But at the same time, this solid, the beaker is also expanding. Yes or no? The beaker in which the liquid is heated, it also expands. So there are two expansions taking place here. One is the expansion of the liquid, the other one is the expansion of the solid. Do we understand this? And therefore, when you see milk coming out, it is not the real expansion of milk, because milk has expanded, but at the same time beaker has also expanded. We call this expansion as the apparent expansion or the observed expansion. Do we understand this? When a liquid in a vessel is heated, the observed expansion of the liquid is slightly less than its real expansion, because along with it, the liquid the vessel also expands. Do we understand this? And therefore, we have two coefficients of expansion. One is coefficient of apparent expansion, and the other one is coefficient of real expansion. We have already seen the coefficient of real expansion. Now we will write the formula for coefficient of apparent expansion. I'll give you a 1 minute to note this down. It is in the sheet, but you will have to note it down. Have you noted it down what I said? Well done. Now comes, oops, where is my, now comes the formula for apparent expansion, and as you can guess, the formula is no different. The formula is exactly similar. The only difference being, instead of the term real expansion, we are using the term apparent or the observed expansion. Do you see? The formula is exactly same. The only difference is we are using observed expansion or the apparent expansion. Can I have reason that we understand this? I'll give you 2 minutes to note this down, bacha. That means I can write it in this fashion. I can write it in which fashion? I can write it like this. This coefficient of apparent expansion is nothing but delta V apparent or observed divided by original volume V naught into delta theta. Do we understand this? I'll give you a minute to note this down. Have you noted it down, bacha? Yes, now the question comes, what is the relation between the two? This is the relation between the two. I hope you can see this. Gamma real, which is the real coefficient of expansion, will be equal to gamma A, which is the coefficient of apparent expansion, plus gamma S or gamma G or gamma V, where gamma S or gamma G or gamma V is the coefficient of volume expansion of the vessel. So coefficient of real expansion of the liquid is always more than the coefficient of apparent expansion. And this formula you must remember, because the question, if it comes, it will be based on this formula and this formula only. Do we understand this? Yes or no? No, yes. Are we there with me on this? Or have I lost you somewhere in between? Note it down, everyone, please. I'll give you a minute to note it down. Have you noted it down, everyone? Then comes the last thing of this expansion, which is the expansion of a gas. Now remember, gas can be expanded. It has two coefficients of expansion. One is known as the volume expansion coefficient. The other one is known as pressure expansion coefficient. The formula is same. The only thing is, in case of volume expansion, it is gamma V. In case of pressure expansion, it is gamma P. So please note down these formulae. I don't think this question can come. You can just note it down in the sheet itself. The formula is similar. You just have to use gamma V or gamma P. I hope you have noted this down, yes or no? Then we come to this last thing, which is always neglected in all the classes that I have seen. It is about dew and humidity. The only thing is, you just need to understand the definition. I don't think a numerical is going to come on this. It is more or less like a free question. What do I mean by a free question? A question which just tests your remembrance of whether you know it or not. It's just like biology. I know that all of you love biology. It's a very simple thing. If you know it, you just take it and you go move ahead. There's nothing that you have to think about it. This is a free question here on humidity. You just need to know the definition and you just need to understand the definition. The question, if it comes, it will be basically on the definition. What is dew? And again, this is more of your field rather than mine. Dew, the water drops obtained by condensation of saturated water vapor are known as dew. You must have seen dew everywhere. You must be seeing IPL. No, you might not be seeing IPL. There are a lot of thing about dew. In the night, dew comes and you see water droplets. Have you seen this? Yes or no? Water droplets condensing saturated vapors. When the gas becomes saturated, what do you mean by gas becoming saturated? We'll come to know about this. Don't worry. So these are all things about humidity. How much is the humidity? Humidity is very high in Mumbai. That's why I don't like that place. Humidity is very high in coastal areas. Kolkata, I studied there. Lot of humidity. I was not able to tolerate that humidity at all. That is why I live in dry climates where I have very less humidity, but I have warm heat currents. We call it loo. That is also dangerous. Humidity. The water droplets which are condensing are known as dews. What is dew point? The temperature at which the water vapor actually present in air becomes saturated and start condensing is known as the dew temperature. Do we understand this? Yes or no? You just have to write the definition. I'll give you a minute to do this. Have you noted this down? Yes, then the next term, which is known as absolute humidity. What is absolute humidity? We hardly use this term, but it is important that we understand the meaning of this term. The amount of water vapor actually present in a unit volume of air. If I take 1 meter cube of air, how much water vapor is present? That is known as absolute humidity. And the unit of this absolute humidity is gram per meter cube. Remember this. Unit of absolute humidity is gram per meter cube. The dimension is kg का k और mass का m per l cube, m by l cube, something like density only. Do we understand this? Please note down this absolute humidity. The actual amount of water vapor present in a unit volume of air is known as absolute humidity. Have we noted this down? Yes or no? No, yes. Shall we move ahead? Well, instead of absolute humidity, the term that we use is relative humidity or RH. Now, relative humidity is basically a percentage or a ratio. And how do you understand this percentage or ratio? For example, if at this temperature, right now the temperature here is 35 or 36 or maybe 40 degrees. At this temperature, 35 or 36 or 40 degrees, let us say 5 grams 5 grams of water vapor is required to saturate this air. If 5 grams of water vapor is present, this air will become saturated. Let us say for an example. Now, what is the actual amount of water vapor present? Let us say it is 4 grams. 4 grams is present in the air right now and 5 grams is required to saturate the air. The ratio of 4 by 5 in percentage, the amount of water vapor which is actually present to the amount of water vapor which is required to saturate that ratio. Right now, if I say 4 is to 5, 4 by 5 or 80% or 0.8, that is the relative humidity at this place. Do we understand this? In Mumbai, in Kolkata, at one point in time when I was there studying, I remember very vaguely that I went to have a shower. I came out of the shower and I was again sweating. The humidity, not the humidity, the relative humidity at that point in time was 98%. 98% was the relative humidity. Too much. The actual amount of water vapor present divided by the amount of water which is required to saturate is known as relative humidity. Do we understand this? If the relative humidity is very less, it is a dry climate. Right now I am in my hometown. The climate is very dry. The humidity is not that much. If you are in a coastal region, the humidity will be much more because sea is near to you. The air which is coming is carrying the water droplets with it, and that is why the humidity is pretty high. Do we understand this? Or it has gone above our head saying bye bye, we are going, don't worry. Have you understood relative humidity? Yes or no? You will never come across the term absolute humidity. No one understands what is absolute humidity. The only thing we understand is relative humidity. And these are the 2 points. It is actually expressed as a percentage. So someone says that the ratio is 0.8. It means 48% for saturated air. The relative humidity would be 1 or 100%. Do we understand this? Yes or no? No, yes. Please note this down. Fatafat. Have you noted it down, bacha? Shall I move ahead? And we move ahead to the last part of this particular topic, I should say, chapter, thermodynamics. Because on the next class, we would be starting with heat transfer. And with that heat transfer, we will be finishing this entire topic of thermodynamics. The other definitions of relative humidity, please don't try to make sense out of it. Just remember this. Relative humidity is vapor pressure of air. What is the vapor pressure of air right now divided by the saturated vapor pressure when the air becomes saturated. Right now, what is the vapor pressure divided by what is the value of air when the air is saturated or saturated vapor pressure, or you can define it in a different way. Saturated vapor pressure at dew point divided by the saturated vapor pressure at the given air temperature. On a rainy day, what happens? Why do we have rain? Because the relative humidity becomes 100%. At room temperature, it becomes 100%, and that is why water vapor starts to condense. Do we understand this? Nare, do we understand this? Note it down, fatafat. I hope you have noted this down, beta. Now, remember, this sheet is over. From the next class, we'll be starting with the sheet on heat transfer. At the end of this sheet, on page number 64, you will see memory tips. Memory tips means the entire course, entire curriculum given in very, very short points. So when you want to revise this topic, you can go through these memory tips. Everything that we have discussed, almost everything would be there in those memory tips. As you can see, if I just scroll down, everything that we have done is memorized in two sheets. So that is how you can quickly memorize it. I hope you have noted down everything in the sheet that you need to remember. On that note, I will take a pause and we'll meet in the next class. We'll meet with heat transfer. Take care and have a very nice day.